In the previous lecture, we have seen the deduction of Fermat's principle from laws of reflection of light, and we have also seen the deduction of Fermat's principle from deduction of laws of reflection of light from Fermat's principle. Now today we are going to discuss Fermat's principle and laws of refraction of light. So again we will see, if we will assume that Fermat's principle is valid, then we can establish the laws of refraction of light. But when you will consider that the laws of refraction of light are valid, then you will be able to establish Fermat's principle. So for this, let us see this figure. You can see I have assumed here actually two fixed points situated in two different media. First one is A and another point is B. Point A is situated in a medium having the refractive index N1. Actually this first medium is a homogeneous medium, so refractive index N1 of this medium will be throughout same. And similarly the second medium has a refractive index of N2 and it is also a homogeneous medium. So the refractive index here changes discontinuously. Whenever you will move from first medium to second medium, only then it will change. But in a particular medium, that is the first medium and the second medium, this refractive index is everywhere same. So this is just an example of variation of refractive index in discontinuous manner, not continuous manner. Now consider a light ray starts moving from point A to point B, but it moves to A to B via O. Actually this point O lies on a surface ML, you can see in this figure, and this surface ML actually separates the two media. So point O lies on this interface. And I have drawn a normal NN prime, you can see in this figure, at the point O. And so in this condition you can say if AO is the incident ray and ON is normal, then this angle I between the incident ray and the normal is angle of incidence. And in second medium, OB is actually the refracted light ray, and the angle R between this refracted light ray and the normal is actually angle of refraction. Now let us drop normals or perpendiculars from point A and from point B on the interface. So you can see AM is a perpendicular drawn from point A on the interface ML, and similarly BL is the perpendicular drawn from point B on the same interface. Now since point A and B are fixed, so definitely the M and L will be also fixed because A and B are fixed. So I have assumed that the distance between M and L, that is ML, is actually constant, and that constant is equal to D. Now this point O may be anywhere on this interface, so we can consider that this point O is situated at a distance x from the foot of the perpendicular AM. So you can see in this figure I have considered that this OM is equal to x. And if OM is equal to x, it is clear from the figure that this OL will be equal to D minus x, because distance between M and L is D. So OL will be D minus x. Now the path length covered by this light ray in the first medium is AO, which I have shown by L1, and in the second medium it is OB, and I have assumed it L2. Now you can see from this geometry of figure that what will be L1. You can see easily this L1 will be simply equal to A square plus X square square root. And similarly, what will be L2? L2 will be equal to B square plus D minus X whole square's square root. This is L1 and L2. But can you say if L1 is the path length in first medium whose refractive index is equal to N1, then what is the optical path? As I have told you in the first lecture on Fermat's principle, that if the medium is homogeneous and you want to calculate the optical path, what we do? We simply multiply the refractive index of the medium and the path covered by the light in that medium. That product actually gives the optical path. So when you will find the optical path, we will simply multiply N1 and L1 in first medium. And similarly in second medium, the optical path will be the product of N2 and L2. Now let us calculate these things. Actually, for your convenience, I have written all these things which I have explained on the basis of that figure here, and so you can see all these things has been mentioned here, and this will be very helpful to you to write the correct answer or the languages. So you can see here the optical path. The optical path described by light. Described by light in moving from A to B via O. If we consider that this optical path is L, what will be this L? L will be N1 into L1 plus N2 into L2, because the product of the refractive index and the actual path length of the light ray gives the optical path. And you have seen that this L1 is equal to a square root of A square plus X square, and similarly L2 is equal to a square root of B square plus D minus X whole square. So this is actually the optical path covered by our light in moving from A to B via O, with the point O actually lies on the interface which separates the two media. Now you can see that this is optical path. Now according to Fermat's principle, this path must be extremum, and so to know the condition of extremum, first of all we will differentiate this L with respect to X. Why we will differentiate L with respect to X? Because you can see that the point O in this figure has been selected arbitrarily. So its distance from M to distance X of this point from M is actually arbitrary. So you can see that this L is a function of X. So first of all we will see how this L will vary with respect to X. So as L is equal to L of X, L is a function of X, so we can find what will be the value of dl by dx. dl by dx. You can see this will be simply d dx, and let us put the value of L here. This is n1 root over a square plus x square and plus n2 root over b square plus d minus x का whole square. This is just a simple differentiation. You can do it. You can see this will be simply n1 1 over 2 a square plus x square to the power 1 minus 2 1 by 2 minus 1 and into 2x, and again here n2 times 1 by 2 into b square plus d minus x whole square and whole to the power 1 by 2 minus 1 into 2 times d minus x and again minus 1, because dc of x will be 1, and as here is minus sign, so this will be minus 1. So now you can see this number 2 and this 2 will cancel out. Similarly, this 2 and this 2 will also cancel out. So after simplification, you can see what will be this dl by dx. It is easy to see this equation and write it in a particular manner. Then you will see this is simply x over root over a square plus x square. I have written this sign of a square root instead of 1 by 2, and minus d minus x over root over b square plus d minus x whole square. Now see the geometry of this figure. You can see here, as this angle is I, so this angle OAM will be also I. Why? Because you know ON is normal to this interface and AM is also normal to the same interface. So these two normals AM and ON will be parallel, and AO is intersecting these two lines. So definitely, according to geometry, this alternate angle will be equal. So angle OAM, as I have shown in this figure, is also I. And if I ask you what will be sine I, you can see sine I will be simply x over this L1, and L1 is root over a square plus x square. So x over root over a square plus x square is simply sine I. And similarly, you can see when you write d minus x over this L2, L2 means this, root over b square plus d minus x whole square. So that will be simply equal to sine r. So you can see that we can replace this x over this much by sine I. Here actually there is also the term refractive indices n1 and n2, so you must write it. So here will be n1 and here is n2. So this will be simply n1 sine I minus n2 sine r. Let us say this is equation 2. Now after getting this result, we can establish Fermat's principle. If we consider that our laws of refraction of light is valid, or we know it. So first of all, we will find the Fermat's principle from laws of refraction. So Fermat's principle from laws of refraction. As you know, according to Snell's law, which is actually the second law of refraction, this n1 sine I is equal to n2 sine r. So according to Snell's law, according to Snell's law, n1 sin I is equal to n2 sin R. So, if this law of refraction is holding here, then you can see from this equation 2 what will be dl by dx. So, from 2 we can see that this dl by dx is simply equal to 0. And if dl by dx is 0, then you can see this L will be what? This L will be extremum. And L is extremum. This is actually the Fermat's principle. Because you know, according to Fermat's principle, when a light ray travels from a fixed point to another fixed point, then the actual path of traverse of the light is actually extremum. It means this is either maximum or it is minimum. Although when we will actually evaluate the second order derivative of this equation, second order derivative of this equation, you can see here, that is this equation 1, not equation 2. When we will evaluate if d2l by dx square is evaluated from 1. In fact, I am not evaluating it, it is just homework for you. Find the second order derivative from equation 1 of L, then you will find that d2L by dx square, you will see that this will be actually equal to positive, greater than 0. And if it will be positive, it means what? This L will be minimum. So as I have told you earlier in the statement of Fermat's principle, that when refraction and reflection takes place from plane surface, then actually the condition of minimum path length holds. So you can check it. So definitely you have to evaluate the second order derivative, and then you will see that this second order derivative of L will be greater than 0, and that implies, according to calculus, that this L is minimum. So in this case L will be minimum. So you have seen that if we consider that our laws of refraction of light, that is Snell's law, is holding here, then you can easily derive Fermat's principle. So this is actually the derivation of Fermat's principle from laws of refraction of light. Now we are going to discuss the reverse problem. That is, now we will establish laws of refraction of light from Fermat's principle. So laws of refraction from Fermat's principle. As you know, according to Fermat's principle, L should be extremum, and if L will be extremum, can you say what will be dl by dx? Definitely you can say this, if L is extremum, then this dl by dx will be equal to 0. Now put the value of this dl by dx which we have obtained in equation 2. You can see here. In fact, dl by dx is equal to n1 sin I minus n2 sin R. So put it here. So this is n1 sin I minus n2 sin R, and this is equal to 0. And so you can say n1 sin I is equal to n2 sin R. Can you say what is this? This is nothing. This is simply a Snell's law, or the second law of refraction. This is a Snell's law. So you have seen how we can prove or how we can derive the laws of refraction of light from Fermat's principle. But this is actually the second law of refraction of light, which is known as Snell's law. We can also establish the first law of refraction of light, which actually tells that the incident ray, refracted ray, and the normal at the point of incidence are coplanar. So you can see logically here that if the lines AO and OB, see here, see this figure. If this lines AO and this line OB intersecting at this point O will be always in one plane. And so you know by Fermat's principle, the path AOB from A to B via refraction at O should be minimum. And this can only happen when the point O on the interface ML is such that the plane AOB is normal to the interface ML, because in minimum condition, you know, the distance between 2 points is shortest, and so definitely the plane through AOB will be normal to the interface ML. And this plane will also contain this normal ON, and ON, which is actually normal to the interface at O. So in this way you can say that the first law of refraction is established. So there is I have not written these things, but I hope you have understand that since AOB will lie in same plane, and that plane will be definitely perpendicular to the plane containing ML, because AOB is the shortest path, and in fact in a plane which will be normal to the plane of AOB, that also contains ON. So in this way you can say that the incident ray AO, refracted ray OB, and the normal ON, all these three lie in same plane, or they are coplanar. So in this way we have actually established the laws of refraction of light from Fermat's principle, and also we have actually established the Fermat's principle from laws of refraction of light. So I hope you have understand each and every step clearly. So this was actually a very simple application of Fermat's principle. Now in fact in the forthcoming lecture we will see some of the rigorous applications of Fermat's principle.